Assalamualaikum warahmatullahi wabarakatuh. We are from Group 6. We'll present our assignment project entitled FSK and Qpsk as a modulation technique. First of all, my name is Mohammad Arfan bin Khairol Annuar. I will explain a little introduction for FSK and Qpsk. What is FSK? Frequency shift keying is a digital modulation technique in which the carrier signal frequency shifts in response to changes in the digital signal. FSK is a frequency modulation method. For a binary high input, the output of an FSK modulated wave is high in frequency, and for binary low input, it is low in frequency. Mark and space frequencies are the binary ones and zeros. What is Qpsk? Quadrature phase shift keying is a type of phase shift keying. Unlike BPSK, which is a DSBCS modulation sim with digital information for the message, Qpsk is also a DSBCS modulation sim, but it sends 2 bits of digital information at a time. The amount of radio frequency spectrum required to transmit Qpsk reliably is half that required for BPSK signal, which in turn makes room for more users on the channel. Next, I will leave it to the next presenter.
Assalamualaikum and hi. My name is Mohammad Emil Haziq bin Mohammad, and in this video, I will explain and simulate the signaling for both FSK and Qpsk modulation and demodulation. But for now, we are going to focus on FSK modulation and demodulation. As we can see here, this is the design block for FSK modulation and demodulation. The blocks that I use are Bernoulli binary generator, sine waves, switch, charge pump PLL, relational operator, constant, and scope. Each of these blocks here has their own purpose. The Bernoulli binary generator is used to generate a random binary number as the input. It means that every time we try to run the simulation, the input will always be different. So when we try to run the simulation, the Bernoulli binary generator will generate a random binary number, which can be 1101, 0100, 1101, or etc. The sine wave blocks here act as the frequencies for the signal. We use 2 here because there's going to be 2 different frequencies. We're going to check on that later. The input will go through the switch, where we set the threshold here as 0.5. So if the input is 1, the switch will allow the top sine wave to go through. And if the input is 0, it will allow the bottom sine wave to go through. The charge pump PLL here acts as the demodulator along with the relational operator and constant. And the scope is where we see the signals generated. So we run this simulation here. And these are the signals generated through the scope. And the top one here is the digital input signal. The input here, this one is generated by Bernoulli binary generator. The input is 0, 1, 1, 1, 0, 0, 0, 1, 0, 0. And the middle one here is the FSK modulated signal. As I said before, there's going to be 2 different frequencies, as we can see here. So when the input is 1, the frequency is higher compared to the frequency here when the input is 0. This is what we call mark and space. Mark is when the input is 1, and space is when the input is 0. It has 2 different frequencies. And the bottom one is FSK demodulated signal. The output and the input is the same, but with a little bit of delay. We moving on to the next simulation. This is the design block for quadrature phase shift keying. or well known as Qpsk modulation and demodulation. The blocks used are completely different from before, the FSK modulation and demodulation. You will have random integer generator for the input source, Qpsk modulator and demodulator baseband, the AWGN channel, complex to real imaginary sine waves, products, add, constellation diagram, and scopes. So the real question here is, why do we have all these blocks below here? This is because the modulated wave generated by this block is in complex digital form. We are used to see the signal in sinusoidal waveform because we can properly see the phase shift. So in order to do that, we have to split the complex to real and imaginary parts. The real part need to be multiplied with sine wave, and the imaginary part need to be multiplied with cosine wave. So these two blocks here, the top one is for sine waves and the bottom one is for cosine wave. And the total product from both parts here need to be added together to generate a single sinusoidal waveform. And the constellation diagram here used to analyze the performance after the modulated wave receive the noise from AWGN channel. So when I run the simulation here, we can see here that there are 4 points here. Okay, we can see 4 points here, and these yellowish dots here is the noise from the AWGN channel. What we need to focus is that the dots here is focusing on this red dots here. It doesn't spread too much, so it means that our Qpsk modulation and demodulation is working fine. Okay, now we need to see the signals generated for the input and output. Here is the input signal, and below here is the demodulated wave. We can clearly see that both waves are identical. It means that our Qpsk modulation and demodulation is working fine. And now we need to see the modulated wave here. This is the sinusoidal waveform generated after we split it, the real and imaginary parts. When the input doesn't change here, you can see here, the wave is in a normal state. But when the input change, we can see that the phase shift occurs. So this is our Qpsk modulation and demodulation.
For a conclusion, FSK has a lower probability of error and has higher immunity to noise due to the constant envelope. FSK signal tag may be different from depending on their intended application, whereas binary FSK is the simplest of them. With the increasing sophistication of electronic and signal detection theory, it is clear that FSK modulator and demodulator can be utilized to optimally demodulate the many different digital signal formats. Qpsk is capable of transmitting data twice as faster as BPSK with the same energy per bit. In this project, we will also learn in the future that Qpsk has half of the bandwidth of BPSK. That's all from our group. Thank you.